It was a real pleasure to be visiting Hawaii, the number one place someone wants to go to be able to do science. I'm talking today about something that was originally meant to be a project for 3 University of Alabama undergraduate students to work on as part of their year-long project to work in their free time. When working with undergraduates, you never quite know what you're going to get. Sometimes they do great and they're highly motivated and they get a lot done and you get something that you can publish. Other times, perhaps they get bogged down with their other classes, they can't donate a lot of time to the project, and you really don't get anything useful. So you have to be careful of what kind of project you give them. On one hand, you want to give them a project that they are going to be interested in, an interesting topic for them to work on, but you also have to be prepared for the fact that you may not get anything done out of that project. So the project that I gave them was on looking at X-ray sources in nearby galaxies. And I'm happy to report that this project went way beyond expectations. It actually led to a publication in Nature recently based on this work that started out as an undergraduate project. So I'll be talking about giant X-ray flares in nearby galaxies. Very large, high amplitude, high energetic flares that happen in a pair of nearby galaxies, not at the center. We're not talking about supermassive black holes at the center. We're talking about in the outskirts of 2 particular galaxies for which we found evidence for these flares. Now, I'm going to begin with a very rudimentary and quick discussion about X-ray binary stars. Right? An X-ray binary star, you can see here in the little illustration, kind of shows the geometry of such systems. You have a compact object, either a neutron star or a black hole, that is effectively stealing material from a companion star, a normal star, red giant or subgiant, or maybe even a main sequence star. You need a very tight binary for this to happen, for the compact object and the star to get close enough such that material from the outer layers of the normal star go through the inner L1 Lagrangian point of the system. That material starts feeling the gravity from the compact object more than it does its host star, and it's funneled through into and falls towards the compact object. Now, because the gas lost from the star has angular momentum from the orbit, it can't fall directly onto the compact object. It goes into because of conservation of angular momentum, it goes into a holding pattern, which of course we call an accretion disk. Now, at each radius in the accretion disk of this flattened disk, the gas is going around at its own local Keplerian velocity. So you have slight velocity differences between adjacent particles of gas. And this leads to friction between adjacent parcels of gas. It has 2 effects. First, it can redistribute the angular momentum, sending some of the gas out of the disk and other gas into the disk, which will eventually fall onto the surface of the neutron star or through the event horizon of the black hole. It also has the effect of friction of heating up the gas to very high temperatures, 10 million Kelvin or more, up to X-ray emitting temperatures, making these systems extremely bright X-ray sources. In fact, the brightest X-ray sources in our sky are X-ray binaries that reside within the Milky Way. The Milky Way has about maybe 150 to 200 X-ray binaries composed of either neutron stars or black holes that are stealing material from a nearby companion. Now, this studying X-ray binaries in our galaxy goes all the way back to the beginnings of X-ray astronomy in the 1970s. It's only been since the launch of Chandra and XMM that we can start seeing X-ray binaries in nearby galaxies. This shows one example of a nearby elliptical galaxy, GC 1399, that has a very rich collection of X-ray binary sources. Over on the left is the Chandra image of this galaxy. So in addition to having hot interstellar medium at the center, that's that diffuse emission, you see a collection of point sources in the X-rays, nearly all of which are accreting neutron star or stellar mass black hole binaries. A few might be background AGN or foreground Milky Way stars along the line of sight to this galaxy, but statistically speaking, most of the point sources you see there actually reside in the galaxy NGC 1399 of 20 megaparsecs. Now, after Chandra was launched, it became fashionable to compare the positions of these X-ray sources to optical images, for example, HST, shown here on the right. And what's found is a rather large percentage of these X-ray binaries are found within globular clusters of the host galaxy. Highlighted one such source here, perhaps you can't see it in the blue circle, one luminous source that we've worked on in the past. This shows a blow-up of it. If you match up the optical and the X-ray, you see that many of them are coincident with a point source, or what appears to be an optical point source. That's actually a globular cluster of that galaxy. I mean, if it were at a few kiloparsecs, it would look like something like M13 in our own galaxy. But at 20 megaparsecs, even Hubble cannot resolve these globular clusters into extended sources. They still appear like point sources. You need to do the broadband imaging, broadband colors, or even better, spectroscopy to determine whether that is a globular cluster with the correct recessional velocity to be orbiting this galaxy, or whether it's a background AGN or there's a foreground Milky Way star. Now, it wasn't all unexpected that some of these X-ray binaries would be found in globular clusters. Within our own Milky Way population, about 10% of the X-ray binaries are located within one of the Milky Way's 150 or so globular clusters. Despite the fact that globular clusters only contain about 0.1% of the number of stars in the Milky Way. So globular clusters are about 100 times more likely per unit luminosity to host an X-ray binary than within the field of a galaxy. And this is generally understood in terms of dynamics of the high stellar density within globular clusters. You need a very tight binary to get this mass transfer to happen. So either through three-body interactions, you can tighten a lot of existing binaries to the point where you make an X-ray binary about 100 times more frequently in a globular cluster than you would out in the field with a similar number of stars. So in Milky Way, about 10% of X-ray binaries are found in globular clusters. For some large ellipticals, which contain a much larger number of globular clusters per unit light, it can be even higher. For example, for NGC 1399, the galaxy we just showed, about 2/3 of the X-ray binaries that were within the Hubble with VIC-2 field of view, about 2/3 are found within globular clusters. So in fact, the majority of X-ray binaries in large elliptical galaxies are found within a globular cluster hosted by the particular galaxy. Now, the reason why I go into this is the original goal of the project was to try to find X-ray binaries, and specifically X-ray binaries that had a black hole as a primary, as the accreting object in a globular cluster around these galaxies. Because we're not at all sure that globular clusters harbor black holes at all. Right? Among the 15 or so X-ray binaries in globular clusters in the Milky Way, every single one of them is a neutron star binary with a companion. None of them are black holes. And we don't know whether that is just due to small number statistics. Neutron stars are more common than black holes. Maybe you expected one or two within the entire Milky Way globular cluster population, you found zero. Or maybe it's telling us something physically interesting. Some simulations show that black holes should be dynamically ejected from globular clusters earlier in the history of the globular cluster, and maybe there aren't any black holes left, or maybe a very, very small number of black holes left within globular clusters, naturally explaining why we don't see any within the Milky Way's globular cluster population. We'd like to go to other galaxies and use the large globular cluster population of them to try to answer this question.
Why would a black hole be ejected from a cluster?
Early in the history of the globular cluster, you would get mass segregation. So all the heaviest objects would sink to the center and basically form their own isolated system where they would interact only with one another. So massive objects interact with other massive objects. You have all the black holes sink to the center. One by one, they would kick each other out till you're left with only a very small number left in the center. That's the working theory as to how you would get rid of these how do you get rid of these black holes. They don't interact with the low mass stars. They only interact with one another and kick each other out via multi-body.
So they should be residing in the centers as well, the ones that are left?
Yes. You might expect it to sink to the center. But we don't see any in the Milky Way's population. The meager globular cluster population, we don't have a lot to work with, which is kind of motivates looking at nearby galaxies.
There was dynamic evidence for a fairly massive black hole in a globular cluster found fairly recently, though, right? I forget who, R.V. Loeb and collaborators.
In Milky Way population?
I can't remember if it was in the Milky Way or outside.
The argument for an intermediate mass black hole, like 1,000 solar masses black hole, that's been going on for like 40 years in the literature. You have one group that says we find dynamical evidence from the stars that they're orbiting something massive. Another group comes back and say, no, you can model that a different way. They've been going back for decades as to whether you get an intermediate mass black hole in the center. So that was another motivation here is if you find a black hole, is it stellar mass or is it intermediate mass? Intermediate mass would be particularly interesting because if you scale down the relation between the mass of the bulge of the galaxy and the supermassive black hole, if you extrapolate that into the globular cluster regime, you would predict a black hole of say 1,000 to 10,000 solar masses. So that would be interesting to find. But these two camps have been at each other's throats, I think, for decades now. They can't really decide whether there's an intermediate mass black hole in the center or not. So yeah, that's still an open question that's been going on for quite some time. So Using the globular cluster populations of other galaxies, the idea was try to find X-ray binaries that were very luminous that could kind of be a earmark for finding black holes that are in these globular clusters. So well, you need to find a way to distinguish a neutron star binary from a black hole binary. Given the fact that these systems are so far away, you can't ever do any dynamical observations of the star, the secondary star going around the compact object. We have to use energetic arguments in order to try to answer this question. This comes down to the Eddington limit of compact objects. The Eddington limit is the maximum amount of radiation that a compact object can emit. You cannot throw an arbitrarily large amount of material onto a compact object and get an arbitrarily large amount of radiation coming out. Eventually, you'll reach a point where radiation pressure will blow away any additional matter that's trying to fall on, sort of a self-limiting matter that scales with the mass of the compact object. So for a neutron star, you don't expect them to be more luminous than their Eddington limit, which numerically is about 2 × 10⁻38 ergs per second. Anything more luminous than that might require a black hole instead, with a higher mass, correspondingly higher mass to get up to correspondingly higher luminosities. So you can find a source that's 10⁻39 ergs per second, 5 times the Eddington limit of a neutron star. You have better confidence that that's a black hole binary rather than a neutron star binary. Now, there's one problem with that, in that these systems are far enough away that you can't resolve them. If Hubble can't resolve these globular clusters, Chandra certainly can't resolve these. So you may have, you could have 5 sources packed together in the same globular cluster. They're all at this limit. You could have 5 neutron stars masquerading as a single 10⁻39 ergs per second source. You may be fooled into thinking that that's a black hole rather than a neutron star, but really you're seeing 5 different sources. So one way around that is to look for variability. Okay, if you see an object that varies in its X-ray flux by factors of 2 or more, that's probably going to be a single object. You couldn't get 5 objects to all vary together coherently to change the luminosity of the object. You can find an object that's 10⁻39 ergs per second and it varies a lot. You can be assured that that's a single source. Most likely it's going to be a black hole instead of a neutron star. Yes?
Eddington limit is really for a spherically symmetric system, right? There was a lot of discussion about this at the XMM meeting last week. So the reason for the discussion was that some systems have been shown to violate the Eddington limit by like factor 10.
Yeah.
So it's just another.
It's not an airtight way of finding black holes. That's definitely true, but it's a starting point. Mm-hmm. One other fly in the ointment is there have been neutron stars. They're pulsars. They've been discovered to be pulsars. We know the neutron stars that have gone up more than 10 times the Eddington limit of a neutron star. So that's a problem. At the time we started the project, that hadn't been found yet. So we kind of started with the luminosity argument and say, let's start here. Can we find luminous objects that exceed neutron star limit by factors of several? But you're exactly right. Even the luminosity argument is not airtight. Some of them could be neutron stars. Fortunately, the main result of this work doesn't rely on them being neutron stars or black holes. It's finding a new phenomenon.
Right.
So fortunately for me and for this project, it doesn't rely heavily on them really being black holes. Now, this idea of looking for variability, it wasn't a new one. The first time back in 2007 by Macaron and colleagues in a globular cluster in NGC 4472 in the Virgo cluster, shown there inside the green circle. This is a source, X-ray image taken with XMM Newton. This is its X-ray light curve, and you can see how it varied dramatically over the 80,000 second XMM observation. It started out very luminous, 20 times the Eddington luminosity of a neutron star. But over a course of just about an hour, a few thousand seconds, it dropped in flux by almost an order of magnitude. So clearly we have a single object here. This is not a collection of fainter sources in the same globular cluster. This is one object. And this was touted at the time. Again, this was 10 years ago, so before a lot was known about can neutron stars really violate their Eddington limit. This was touted as the first example of a black hole within a globular cluster. And a few more were found along the way from that point on. The idea of the project that the undergraduates at Alabama would work on was try to find more objects like this. At least that was the original goal. Now, since I know this is primarily an optical audience, you may or may not be familiar with how X-ray data collection differs from optical. So I'll just mention just a few details. X-ray fluxes and X-ray photon rates from objects are really, really low. So each photon matters, and each photon is babied. We don't want to throw out any photon, we don't have to because there just aren't that many for most X-ray sources in the universe. So each photon that hits the detector is tagged with three quantities, the X and a Y position. So you can recreate an X-ray image, the RA and the DEC. You can determine the energy of the photon. So if you have enough photons, you can derive an X-ray spectrum for that source. And crucially for this particular project, we can get an arrival time of that particular, each photon that comes in is getting tagged with the time. Now the time is, your time resolution is set by the observation itself. For very, very luminous sources, bright sources, you can have the readout time be much shorter, down to fractions of a second. But for typical normal Chandra or XMM observations, the time bins are about 3 seconds. So for these galaxies we're looking at, these sources we're finding in galaxies, we're getting time resolution at about the 3-second level. We can derive light curves from that. That's just fine because for most sources, you get one photon every few hundred seconds. So having 3-second bins is really not a problem in terms of getting a useful timing information out. Now, if you have a lot of photons, and this is a light curve an X-ray light curve I just grabbed off the internet from a bright source, you can do traditional time binning techniques. Within a given time frame, you count up the number of X-ray photons that were detected, you have a count rate uncertainty. You can see, for example, large variability for this particular source shown in this image here. Right? This is all fine and dandy if you have lots of photons, thousands or tens of thousands of photons for one source. You can bin them up, you can have a number of independent time bins. Problem is, when we look at X-ray binaries in nearby galaxies, we're at really low count rates. Even the most luminous point sources we see here are going to give you a couple hundred photons. And the fainter ones, only a few dozen photons. Doesn't really make sense to make a light curve out of 20 photons, 50 photons. You're not going to get enough resolution. You're not going to see any variability by binning them in equally spaced time bins or something of that nature. So we need to come up with somewhat more creative techniques for finding variability for sources that aren't emitting very many X-ray photons to begin with. So what we do is, again, we don't want to throw away any photon. On a photon by photon basis, we can try to look for either bursts or a dearth of photons over a given time frame to see if we can find large-scale variability. Now remember, we're trying to find objects that are variable and reach 10 to the 39 Earth per second at some point in the observation. So one way to do that is to look for short bursts of X-ray emission over a short time frame to reach that threshold of 10 to the 39 Earth per second while using every photon that we have. So we use what we call cumulative photon arrival time plots, right? Now I'm going to show several of these throughout the talk, so I'll spend a little time here describing exactly how these work. Let's take a random source, the image that's shown up there in the white circle. This particular source had about 130 photons detected over about a 40,000 second Chandra observation, so about half a day, 12 hours or so. 130 photons were detected, so that's once every 300 seconds or so, you're getting a photon being detected. Now what we do is we start at time zero. First photon comes in, short time after that. And then the second photon comes in about 300 seconds after that. And we build this cumulative function of when the times are coming in, when the photons are coming in. Now, for a non-variable source, it's going to come in roughly once every 300 seconds. You would expect a linear a line that's roughly constant slope everywhere, right? This would be what we would call an uninteresting source, not a lot of variability. It has little bumps and wiggles, but that's just due to Poisson noise, counting statistics as they come in. We ran statistical tests to determine whether any type of flare was due to Poisson fluctuation or was real. Basically what we did is we first looked for a photon burst of 4 photons. We compared the arrival time from photon 1 to photon 4. Those 4 photons came in what time interval? How did that compare to the average count rate? If it was statistically significant, we set it aside to look at. If it wasn't, we move on. We go to photon 2 versus photon 5, photon 3 versus photon 6. We look for 4 photon bursts all the way to the top and see is there any 4 photon burst in a time short enough to make it statistically significant. Then we come back and we do 5 photon bursts, and then 6 photon bursts, all the way up to 20 photon bursts. So we were looking over a variety of photon burst scales to try to find something that was indicative of a flare rather than simply a small fluctuation in count rate due to Poisson noise. And we would do that for every point source in the field of view. Of course, this was all automated. I didn't make the poor undergraduates do this by hand one by one. But we could go through these with some scripts that we wrote, trying to find something that was statistically significant in terms of the burst rate over a very short period of time that might be missed by more traditional methods of trying to find variability within X-ray sources. So the undergraduates set off to work. A little while later, they came back to me, excited, and they found something that looked like this, right? A lot of photons coming in at the beginning of the observation, but then the source appeared to roll to decrease in flux, and the count rate became lower as time went on, right? So anytime you see this disjoint, you're seeing a change in the count rate. Unfortunately, that excitement lasted for only a short period of time. You realize that people have already published on this one. This was a second example of an X-ray binary that was believed to be a black hole within a globular cluster of this galaxy, NGC 1399. So the technique worked. It found what it was supposed to find, but this one was already discovered by a previous group several years before. They went back to work. They found another interesting one. Nearly 2,000 photons came in a very short period of time. This is a really phenomenal source that people still don't know what it is. But it turns out it was already known by another group. They had found it just a year before we found it. This is some sort of transient source that may or may not be in the 86. There's no optical counterpart for which you can do any spectroscopy, so you don't know how far away it is. Something crazy went on during this time, and then it faded from view, and it's no longer X-ray detectable at all. Again, our routine found this source, but it turned out to be something that was already published. They went back to work, they came back, and they found another one. This one turned out to be quite interesting because it had not been discussed in the literature, at least not the variability. So this cumulative photon arrival plot shows you that the source was not emitting at a constant rate the entire time. Well, the entire observation is about a 75,000 second observation, 162 photons. That's about 1 photon every 500 seconds. So keep that number in mind for the next slide. On average, the source was emitting 1 photon every 500 seconds. Given its spectrum and its distance, that worked out to a pretty high luminosity. It's still 4 times the edge luminosity of a neutron star, but that's not all that rare. We find sources that are comparable to this luminosity all the time in galaxies. Its luminosity alone would not be reason enough to give this source any sort of significance, right? But you can probably pick out by eye that after about 11,000 seconds, this plot goes nearly vertical. And again, verticality is an indicator of flaring. It means you're getting a lot of photons in a very short period of time. So if we zoom in on this, you can actually, if you can see it before, you can see where the flare is happening at about the 11,000 second mark. It goes from constant to flaring, and then back to constant for the rest of the observation. If we want to zoom in on the flare here, we can actually see photon by photon coming in. At the peak, this happened immediately. Okay, you had photon coming in once every 500 seconds or so. Then out of nowhere, you got 6 photons in 22 seconds. The expectation value was 1/20th of a photon during those 22 seconds. So you should have found anything in any random 22-second slice. 6 came in during that time. It's very, very highly statistically significant. It's about 1 in a billion chance that would happen at any time frame. Luminosity approaching 10 to the 41 ergs per second. To our knowledge, this was the most, and this source turned out to be within the globular cluster, we believe. This turned out to be one of the most energetic event ever to happen in a globular cluster that we know of, at least they were defined in the literature. So you see after 22 seconds, the source began to, it was still in an elevated state, but it began to tail off for about 20, 25 minutes or so. It was still emitting way above the Eddington limit of a neutron star, still about an order of magnitude above during its non-flare state, right? But then it died away and it went back right to what it was doing. So if you happen to blink during this 25-minute period, you wouldn't even have known the difference, okay? It was constant, and then it flared, and then it went right back to being constant again. We really weren't sure what to make of it. It wasn't exactly what we were expecting to find. We wanted to find black hole binaries that kind of looked more like one of these, right? Instead, we found, almost by accident, something that looked quite like this, right? So it was an unexpected result as to how this object could change its luminosity by such a large factor. We're talking over a factor of 100 in its flux on timescales of less than 30 seconds.
The one that you showed, just went back to, that was nearly vertical, that was a large change too, wasn't it? Something like that. Was
it was.
Was it because it was closer that it's not as luminous? Or?
We don't, no one knows its distance. Its optical counterpart was variable and it's gone now.
I see.
So it could be a Milky Way neutron star. It could be something else.
Okay. Thank you.
If we knew the distance, it'd be highly exciting, but we don't know the distance of that one. Fortunately for this source, we think we know the distance, or at least we
It's in the cluster.
We might know within a week or so. It has an optical counterpart. So this source, of course, was noted in previous studies back in 2009. Plus and Brown made a catalog of all the X-ray sources, matched them up to globular cluster catalogs made previously by Dersch, and is coincident with an object that looks like a globular cluster. Okay, there's no spectrum of this object, but it has colors and a magnitude that would be consistent with it being a globular cluster at this distance. In fact, some follow-up to the original work in 2005, the Schubert work in 2006, obtained spectra of globular clusters that had, unfortunately, not of our source itself, but of globular cluster candidates that had similar colors to ours. And many of them turned out to be globular clusters. So we have pretty high confidence that this is happening in a globular cluster of that galaxy, not a background AGN, not a foreground Milky Way star that just happens to lie along the line of sight of that galaxy by chance. Right? We would like to get a spectrum of that source. We had a Gemini proposal accepted, Q45 program, which we hope to get accepted, to be undertaken within the next couple of weeks. We could know very, very soon whether the source, and it's down here in field 1, it's around right there, whether that's really a globular cluster or not. We think it is, but it'd be nice to have a spectrum to find absorption lines.
There are globular clusters in the Virgo cluster, which are obvious from the morphology, right? So it's just a small.
This is a fainter one.
Small
yes.
one. Or,
it's our band is like 23. So yeah, it's not a large globular cluster.
I see. So
It's not spatially resolved. Yeah, there isn't any Hubble observation at this point off center. It's too far off to have been included in there. So at Virgo, the larger ones are resolved, or at least marginally resolved, and the fainter ones are not.
And they're all over the place.
Yeah, this is a fainter one. It's not spatially resolved, unfortunately. So we really do need a spectrum. So keep our fingers crossed for good weather. Hopefully we'll have our answer within a couple of weeks as to whether this is truly a globular cluster or not, but we think it is. So that was exciting for the undergraduates to find. They went back to work and they actually found another object shortly after that. This is in a more nearby galaxy, NGC 5128, or SEN8. You can clearly see where the flare is happening right in the middle of the observation. It's chugging away at a very, very modest 4 × 10⁻³ meters per second when the observation began. This is completely garden variety. You would not separate this object from the others for any reason whatsoever. It's rather faint, unremarkable source when it's not flaring. It's about 1 photon every 1,000 seconds you're expecting from this source. But then, just like source 1, you get a nearly vertical rise in the arrival time when the flare happened. It went from 1 every 1,000 seconds to about 1 every 5 seconds, right? A factor of 200 in the luminosity, approaching 10⁻40 ergs per second. Again, out of nowhere, within less than 1 minute, this object changed its luminosity, its energy output, by a factor of 200. Now, fortunately, SEN-A is a very popular target, and Chandra looked at it as part of a 1 million second observation. So there's many epochs of SEN-A spread out over many years. So we went back and looked. I think there are 33 epochs altogether to look through. And we found more flares. This was March 30th, 2007. It was observed 18 days later. Again, this is all by chance. They didn't look at the source specifically. They were just looking at SEN-A in particular, overall. 18 days later was another flare. 1 photon every 3 seconds during the peak. Okay, so we have about a factor of 250 increase in the amount of flux over less than half a minute. And another epoch that was about 6 weeks later, May 30th, 2007, yet another. We're at 1 photon every 3 seconds at its peak. And then again, a year and a half later, in January 2009, another flare. Now this one was really lucky. This was only a 5,000 second observation, which is really short for a Chandra observation. The first photon didn't even come in from the source until the 1100 second mark. Chugged away every 1,000 seconds or so, and then boom, the last 35 seconds of the observation, before Chandra observation cut off, 7 photons came in. So the flare was caught right at the very end of the observation for a 4th example of Chandra finding a flare in this same source. Okay.
In that one, it looks like there were no photons for a significant track.
Yeah, so the first 1,100 seconds, there's nothing. And then here, there's nothing for
Is that
nearly
also,
2,000. Statistically, that's not significant. You expect 1 every 1,000 seconds. Having 1 every 2,000 seconds is
okay. So that was 2,000.
Yeah. But then the last 35 seconds, when they started pouring in, and the observation cut off in mid-flare. So we don't know how long it lasted, but it was caught right at the very end, fortuitously. Now, we tried to make rather crude light curves from these 4 observations. These bins only contain 5 photons each, so the counting statistics the error bars are quite large. But by and large, you can see that these flares look rather similar. If you start at the beginning of the flare at time 0, and then kind of stack them and put them on the same time plot starting at time 0, they look like the behavior is rather similar. They peak very strongly at the very beginning for the first 30 to 60 seconds, and then they tail off over several thousand seconds. So given that these light curves looked rather similar, we tried combining them into one light curve. Again, setting them all equal at time 0. Negative times would be pre-flare times for those 4 observations, and positive times would be post-flare times. And you can see that before and after, the count rate, the luminosity of the source is pretty much the same. Okay? If you're not looking at the right time, this source looks like a constant source that is completely unremarkable. But during that time frame when it's flaring, you get a huge shoot up in the number of counts. By combining the statistics from the 4 observations, we're able to see this a little bit better. Now we take that gray area and we zoom in on it. You can see that the light curve is not symmetric at all. This was the last non-fair light curve. These contain 10 photons now apiece. Once we add them together, we get a huge increase within the first minute. And now with the added statistics of adding 4 together, we can see the flare lasts out to maybe 3,000 seconds or so, maybe about an hour that the flare tails off before going back to its nominal non-flare state. So very fast rise and a rather slow decay after that, lasting about an hour. We'll come back to this a little bit later. The fact that this is not a symmetric rise and fall profile. It looks more like what's called a Fred profile, fast rise, exponential decay. It is sometimes seen in other types of X-ray sources, but definitely not a symmetric rise and fall time for this particular source.
I have a quick question about this. So when you say this is the combined light curve, so is this all the data points just stacked together, or are you averaging in any way? Because I'm just worried, is there one source that's emitting much more frequently and the other ones aren't? Or is that, this is the combined?
Did you sum them or did you normalize them?
Did you sum or normalize?
And then sum.
We summed and then normalized. So the count rates is the.
But you didn't normalize them before you sum. You didn't normalize each one to a peak of 1.
No.
Okay.
But if you look at this, they were all rather similar to begin with. That's what gave us confidence that we could combine them.
Okay.
Individually, they all look very similar. That's why we
So their
combined them.
peak counts rate is about the same.
Yeah, if they were all over the place, we wouldn't try to combine them because then we wouldn't know what we're getting from that. Right. Now we worked together with the Chandra press office to put together this nice color image. This is an X-ray image showing multi-band. The different colors represent different energy bands within the X-ray. Seme is a very beautiful galaxy at all wavelengths, but it has a central AGN. It has an X-ray jet. There's shells of shocked gas here. A ton of X-ray binaries that you see. Our particular source is located over here. There's 2 bright companion sources nearby. That's our source there. This is a little time-lapse image that I put together showing the flare and then the decay. These are not equal time intervals or equal photon intervals. So, but they were normalized to show the correct flux as a function of time. So during the peak, these are going to be very heavily smooth because you're dealing still with a small number of photons. It's extremely bright for that first minute and then decays away to being at this contrast level pretty much undetectable.
It looks like there's a second object on the left.
That's
right at the peak. Is that a
that's
artifact?
smoothing. There happened to be a photon there that got convolved in with the smoothing. That's not a real feature. I wish it were. That'd be really interesting if it were. But that's a function of the very heavy smoothing we had to do because of the limited photon statistics that we have.
Totality and all sorts of stuff.
Yeah. So Chandra found it 4 times. We can also look through the XM observations. It looked at it for a couple 100,000 seconds all combined. And we found 1 flare in the XMM data, again, completely fortuitously after the fact. This was 2014. This was 7 years after the first Chandra observation. So this data sat in the archive a long time. Okay, the source 1 data was taken in 2003. The source 2 Chandra data was taken in 2007. It sat there for 5 to 10 years because the flare was so brief. It's not found by traditional timing techniques. You really have to look at every photon on a photon by photon basis in order to find very, very brief flares like this. But you can see the flare, of course, right here. Very consistent peak with what we found with Chandra, about 10 to the 40 ergs per second, this particular flare when it's flaring. We also work with the XMM press office to put together a little image. This shows an on-off image. So this one here is, and the things look bright, is all the XMM data stacked together when the source was not flaring. And you can barely even see it down here compared to the two comparison sources. But if you only take out the time slices when the source was flaring, it becomes basically the brightest source in the galaxy other than the bright central AGN in the center, comparable to this source up here. It really becomes luminous during that 1 minute or few minute time span when it's flaring. It shows kind of visually how striking this increase in luminosity is between the flaring period and the non-flaring period.
So is that showing variability of the AGN too in this case, or is it just a scaling?
It's a scaling issue.
It's a scaling. Okay.
Otherwise, in order to show these things right, you have to kind of adjust the contrast. So yeah, the contrasts aren't exactly the same just because the AGN in the center is very bright. But, yeah, that's another problem is XMM has a much broader point spread function than Chandra, so things get spread out and it's harder to see the source that we want at a given contrast level. There was some Swift data for this observation, and we found one flare in the Swift data from 2013. So short observation, it was only about 3,400 seconds. When the observation was off, when the source was off, no photons were detected. Swift isn't very sensitive compared to Chandra. So during that 3,000 second time frame, there weren't any photons that were detected. But during the 300 seconds that it was on, got 7 photons, which is statistically significant when you're expecting way, way less than 1 photon. Right? So this is 6 different times this source has been found to be flaring with 3 different instruments. Now, in terms of the optical counterpart, a little more interesting than what we had for source 1, we actually know quite a bit about the optical counterpart. Because SEN-A is so much closer to us, less than 4 megaparsecs, this is its counterpart. Okay, it is what appears to be a globular cluster, a rather luminous one. It's about 17th magnitude, and it's been so well studied in the past that it actually has 2 different names from various studies. So it's been looked at a lot. This montage shows at various wavelengths what the optical counterpart looks like, from ultraviolet to optical to infrared. This HST image is really beautiful. You can see it's actually quite extended, this globular cluster-like object. Its internal velocity dispersion has been measured to be about 20 kilometers per second. Dynamical mass has been inferred of a few times 10 to the 6 solar masses. So it's comparable in mass to Omega Cen in the Milky Way or G1 in M31. So it's a pretty massive object, but it's elongated, which you typically don't see in globular clusters. So one idea is that this could be, rather than a globular cluster, could it be an ultra compact dwarf galaxy? Could it have been a dwarf galaxy that had its outer stars shred away by tidal interaction with the host galaxy itself? Could this be the core of what was the dwarf galaxy? And that's one potential idea to explain what this object could be. So unlike source 1, where even with Hubble, the counterpart was not resolved, we know for sure that this source is at the distance of SEN-A. It is an object that is orbiting SEN-A.
The WISE image there is a different orientation. It's going to the, is it 2 sources or is it I don't understand why the globular cluster would be extended to the northwest in the WISE image and elongated to the northeast southwest and the other. You know what I'm saying?
Yeah, oh, you mean over here?
Yeah. Yeah. Is that too? Why is it?
I didn't make this image, but I would assume that this may be just smoothing, or the PSF. It may be unresolved by wires. What? Yeah.
Is that tail to the tail to the?
To this up here?
Yeah. That's the.
I'm not sure that's real.
I think it's just rotated by 90 degrees because I mean, if you look at the Spitzer image and then compare to the HST
it may not be
CS,
Okay.
it's just it's almost 90 degrees.
Aligned.
Okay.
A colleague of mine put this montage together, so I don't know the details of it, but it's that may be right. It may just be a simple orientation, a 90-degree shift. That's
Or
what.
pixel scale as well, because wide is definitely not.
Yes.
So this is about maybe 3 arc seconds across by per scale.
WISE is.
And Spitzer's got better, I think, resolution than wide. So
Beats that other object. See in the Spitzer image.
it might be that wide can't.
All right, well, to summarize these 2 sources, we can try to get a handle on how frequently they're flaring and how what fraction of the total time are they flaring? Source one, we can't really do a lot. We only have one source. We looked through all the other available Chandra and XMM observations, just that one flare. So when you're working with one occurrence, you can't say a lot about it. It's flaring probably once every 4 days, maybe greater. We don't know, given that the total Chandra plus XMM time was about 370,000 seconds. One flare during that time. Well, we can't say a lot about it, so I won't focus too much on that. Source 2 is a lot more interesting because it flared 6 different times. If you add up all the Chandra, XMM, and Swift data over which we could have found something, it's about 880,000 seconds. It's flaring about once every 1.7 days, if we can assume that this is regular. Now, we do not know whether this is a period or not. All we know is that over a time span of 7 years, covering 880,000 seconds of exposure time, it flared 6 times. So roughly, maybe once every 2 days, you can expect this to happen. But because it's not contiguous, we don't really know whether that's a period or not. Given how the flare lasts about an hour, we're saying it's on about 2.5% of the time, and then off for the remaining 97.5% of the time. So again, if you blink too long, you're not going to see this object flare. But we can at least start putting rough constraints on exactly how often these flares are happening for source 2. So what exactly have we found here? This is a good question, and actually it's one that we're still kind of struggling with. Now, before going into possible explanations, it's good to just step back and think about really how rare this kind of situation is. If you want to talk about objects that are energetic, and by energetic, I'm limiting this to objects that are more luminous than an Eddington luminosity of a 10 solar mass black hole, so above a few times 10 to the 39 ergs per second. Of objects that are that luminous, that vary by factors of at least 100 on time scales of less than 1 minute, it's a pretty short list of known objects in the universe that can do that. And if you further constrain it to objects that don't blow themselves up, because source 2 flared 6 times, it's clearly not blowing itself up. You can get rid of things like supernova and gamma ray bursts. You're left with a very, very short list of potential objects that it could be, if it is indeed an object that we already know about in our universe. And that's soft gamma repeaters and anomalous X-ray pulsars. Now, to cut to the chase, we don't believe that they're either one of these, right? For reasons I'll show in the next couple of slides. We think that our sources are new types of sources, either a new type of source or a new type of accretion mechanism that has not been seen in the meager Milky Way X-ray binary population so far. Now, SGRs and AXPs are basically neutron stars that have very, very high magnetic fields, right? If you have magnetic fields that are embedded in the crust of a neutron star, they can occasionally do a differential rotation. You can twist up these lines and they effectively get a star quake, which rearranges the surface, the crust of the neutron star. That leads to a huge outpouring of energy of very high luminosity for short periods of time. And these have been observed in several sources within the Milky Way. The most energetic ones exceed 10 to the 45 ergs per second, extremely luminous, more luminous than the sources we find. So you don't believe it can be anything like that. There are other lower luminosity SGR and AXPs that are sort of in the range of what we found of our sources, 10 to the 40 to 10 to the 42 ergs per second. So this is one potential explanation for what our sources could be. There's 3 reasons why we don't think that is. First of all, for SGRs in this luminosity range, they're very brief. Okay, these show light curves from Milky Way SGRs. They last only a few tenths of a second. So they flare out and then they're done, right? So the time scales are completely wrong, and the total energy output is completely wrong. Our sources go up to 10 to the 40, 10 to the 41 ergs per second for a full minute, and then decay over an hour. These are just a series of blips, really, of huge amounts of energy over a short period of time. So the energetics don't quite work. Even though the luminosities are similar between SGRs and our sources, the time scales are not. Okay, these are much too short. You would not even detect these at that distance. You wouldn't get enough photons in a tenth of a second in order to tell that there was a flare there in the first place. We think we have something else there. Another idea is that when SGRs and AXPs are not flaring with really low luminosity, okay, they're thought to be individual neutron stars, so they're not accreting matter. They don't get very luminous at all. They're several orders of magnitude fainter than our sources are when our sources are not flaring. Again, how can they get that luminous when they're not flaring, when all the SGRs, AXPs we know in the Milky Way are only 10 to the 34 to 10 to the 36 per second. So again, energetics don't work out when the sources aren't flaring. Now, the theoretical reason why we believe that they're not highly magnetized neutron stars is the physical nature. SGRs, AXPs have a very, very high magnetic field, implying that they're very, very young. And in fact, many SGRs and AXPs are found in regions of very recent star formation. Very massive stars that have only recently become neutron stars still have a very, very high magnetic field that will decay over time. Both of our objects are found in either globular clusters or very red ultra-compact dwarf objects that have not had star formation in a very long time. Right? You would not expect to find a neutron star, a very, very young neutron star, in such an old population, a stellar population like a globular cluster or red compact dwarf. So for those three reasons, we think that our objects are not something we've seen before. The only thing that remotely resembles our sources are soft gamma repeaters or non-centric pulsars. But for these three reasons, we don't believe that they could be. So what exactly have we found here? Right? Well, there's three broad categories that we can discuss. One would be, perhaps we could just, perhaps naively, apply the Eddington limit rule to these sources. If they go up to 10 to the 41 ergs per second, maybe that implies a black hole mass of 10 to the 3 or higher. Right? This would be nice, because it would explain that if you can have intermediate mass black holes within globular clusters. As I said before, if you extrapolate the conformity relation between the bulge of a galaxy and a supermassive black hole at the center, if you extrapolate that down to globular clusters, you would expect intermediate mass black holes in their centers. Is this a case? Is this an intermediate mass black hole that occasionally flares up to its Eddington limit, maybe 10% of its Eddington limit, occasionally by creating matter from a companion? Perhaps. There would be one explanation for that. Another idea is that perhaps it's not emitting isotropically. Perhaps you're having a very narrow beam of material that is sweeping across your line of view every 2 to 4 days, giving the illusion of a high X-ray luminosity. This is probably the least favorite of our scenarios, mainly because of, you think back to the light curve, it was not a symmetric light curve. If you had a beam going past your field of view every 2 to 4 days, you might expect a rise and a fall that was kind of a symmetric Gaussian. We don't see that. We see very fast rise, exponential decay. So in any kind of beaming scenario, you would have to explain why the light curve during that hour-long period was so highly asymmetric and not symmetric as you expect from beam. And then finally, kind of a catch-all shrug of our shoulder explanation. Perhaps these are neutron stars or stellar mass black holes that are doing something in terms of accretion that we just haven't seen before. The meager X-ray binary population of our Milky Way just doesn't contain one of these sources. In fact, we've looked through now over 50 galaxies. We probably looked through over 8,000 sources total, and we found 2. So, perhaps only 1 out of 1,000 or 1 out of a few thousand sources do this. 150 X-ray binaries in the Milky Way just is not a large enough sample size to have found one example of it. So perhaps we're just seeing a type of accretion mechanism that's very violent, does not destroy the object, that for very short periods of time allow a neutron star or a small black hole to violate its Eddington limit by factors of 10 or even 100 by some unknown mechanism at the time. It's work that theorists can perhaps work on and at some point in the future have an idea of what it could be. So I'll just put up my summaries here. I just want to iterate that as far as we know, these are the most energetic events to ever happen in a globular cluster, as they define in the literature. Reaching 10 to the 41 ergs per second by any known means hasn't been observed before for the globular cluster population of the Milky Way or of globular clusters with galaxies in our neighborhood. Very fast, very energetic outbursts from these sources. We don't think that they're SGRs or AXPs, and we're still working on explanations for what they could be. So stay tuned. Thank you.